Hello again, Cons here. I'm recently been doing some testing of the Alatreon armor set bonus, and in order to do some calculations, I needed to know how the elemental boost songs on the hunting horn worked. Well, I wanted to work out how they interacted with Surfy Jiva, and so I'm just doing a little bit of testing now, just to show you what numbers I'm collecting before we go into a spreadsheet. I should warn you, this video is going to get kind of maths heavy, so you can't say I didn't warn you. Basically, what we're testing are the element song up. So we start at 180 element. After the small song, 190. After the large song, 200. And then I guess what I'll do is just quickly play the elemental effectiveness up. That'll give us a number stacked with element large. However, I also need to work out what that is stacked with no element up and also with element up small. But I'll do that off screen. Anyway, I'll meet you back in Spreadsheet Town. This is actually my second time making this video. So that's the reason there's some black bars blocking up some information that I need to get to progressively. I'll put a timestamp for when you can skip forwards just if you want to see certain numbers, but some of them won't make sense until I've explained them, so I've got them blacked out for now. But as you can see here, the numbers that I just got, 180, 190, 200, and 220, and then I also 190 and 210 testing off screen. I also repeated this test for a Zenoga horn, and also some sort of Drakeborn, some dragon horn, I don't know which one it was. But yeah, same values for all of them. I also augmented both horns and repeated the test for each of them, well, for both of those two. What I was interested in is whether or not the augmented element up counts as separate from the base row. So for example, if a horn did like plus 5% element plus an extra 20, I want to know whether or not that would include the augments. And as you can see, it does. We can tell this not from the first values. For example, 450 to 490 and 550 to 590 are both an increase of 40. However, if you look at something like 720 and 900, this is before and after augmenting. Here we got an increase of 60, here we got an increase of 70. And from 720 to 790 versus 900 to 990, those differences are larger. And so what that means is that the hunting horn buffs sort of take into account the augmented increases in defense and actually into element and actually apply to them. So I warned you that this video would get pretty mathematical. So yeah, you've been warned. Feel free to click off if that scares you. I know I probably would. But yeah, I wanted to talk about a few things just before so I can explain what the calculations are and what they mean. First of all, we have this idea of something called true element and true row. Sorry. It's different from the displayed values. The true element is just the displayed element divided by 10. Very simple calculation. And now all of our damage calcs work based on true element. So if you've ever wondered why element always seems to increase in increments of 10, this is it. So for example, if we have an element of, let's say, 720, and we have the LE up 6 skill, which gives you a bonus of 100. You can check this on your own game. A bonus of 100 and also a plus 20% boost. The way this would work is it would take 72. It would work out the true element, which is, 720. The true element, which is 72. It would work out its 20% of that, 14.4. Now, if we add on 14.4 to 72, we end up with 86.4. However, we need to round this. And this is the reason that everything goes in increments of 10. By rounding this, we end up with a value of 86. We then add on the bonus of 100, which obviously in true element terms is actually 10, which gives us 96. And there we know that the displayed element will be 960. This 96 value is what would be used in damage calcs and things like that. So yeah, that rounding is the reason, plus the fact that we divide by 10 is the reason everything seems to go up in increments of 10. So why am I explaining all this? Well, rounding errors and rounding and stuff like that are going to play a huge difference in the calculations that we're about to do. So I just wanted to let you know why and how beforehand and why we're going to be dividing by 10 a lot. So here is my big assumption. The elemental buff from the hunting horn, every single one of them is of the form some multiplier times whatever your element is, plus some flat increase of element. So for example, maybe the small song gives you a 5% increase plus 20 element. I don't know. Or two true element, I should say. Yeah, I don't know the specifics, but we're imagining it's some generic version of this form, and that could cover any range of values. Also, B could just be 0, and it could just be a multiplier, or A could just be 0, and it could just be a flat increase. But yeah, this is a much more generic version that we're going to be working with. Of course, values are rounded, and if A is like a 5% increase, really what we should do is round this, and I'm going to use square brackets as the symbol for rounding. I don't know if that's a standard, but I like that. However, we're also going to make the assumption that the flat increase would be a whole number, like 2, 3 or something like that. They wouldn't add decimals on if they can avoid it. So actually I'm just going to write this as the rounded value of A times E plus B. Very simple. So I'll just do an example. If our element on our weapon is 180, actually we're going to do 18 because we're working in true elements. And let's say we think that A is 5, it's a 5% buff, and B is a 20 flat increase. That's attack up, element up small on the hunting horn. That's our guess. Then, after applying the song, we would end up with the value of 1.05, a 5% increase of 18. Well, actually, we should round that. Plus 2. Again, sorry, B should be a 2. I'm saying 20 elements, so 2 true element. 1.05 times 18 is 4.5, so 22.5 rounded plus 2. 22.5 rounds up to 23, plus 2 is 25, and so your displayed element at the end of this buff would be 250. I do want to mention actually, and I chose these numbers on purpose, 22.5 could also round to 22. It's a bit weird. Monster Hunter World doesn't handle floating point arithmetic very well, and so 0.5s can round up or down, basically depending on luck. I think it's fixed per weapon and setup or something, but it's not consistent throughout the game. Now from our tested values, the 180 element horn at most increased to 220. What this means is that at most B could be 4. That is the biggest. Oh, and by the way, A and B will vary for each buff, of course. Attack up S and attack up large will have different multipliers and different flat amounts. But this 220, which came from effectiveness up, the Echo Wave song, and element up large, together only took us from 180 to 220. And so the max it could ever be is 4. And so I was going to do some complicated maths, and in fact I did in the previous version of the video. It was really long and I did some weird calculus type stuff. But I'll probably post that on. Actually, you know what I'll do? I'll post this paint document and also the original document on Patreon to thank the guys. But yeah, anyway, what I'm actually gonna do is just make a general formula and just test out values of B until it works. I know from hindsight that this will work. There is a more sort of genuine, more rigorous mathematical way of handling these things, but it really bogs down the video, so I'm just gonna skip over it. So we'll do one quick example just to show how the maths works. We had a 450 changing to a 490, and this was from LE up small using the Zinogre horn. We also had a 550 become 590, and this was again LE up on the augmented Zinogre horn. What we're going to do is we're going to run the calcs on this just to see what possible values of A and B could be. So the way we do this is fairly simple. We can write out our equation. We know that 49 is the result of buffing. Must be the rounded value of 45, the original element, times our multiplier increase, plus our flat increase. Now what we'll do is we'll put in test values, and we're going to use 1, 2, 3, and 4 because we know from that's the most it could ever be. Or also 0, of course. And from this, we can say that 45A rounded is 49 minus B. And this is a whole number, of course, because 49 and B are both whole numbers. Now, using some rounding arithmetic, we can solve this for a range of values of A. We can get A is smaller than something and A is bigger than something. Now, just to describe where this approximation comes from, because I want everybody to be able to know that my numbers are accurate and replicatable. If we draw the line of A, and then let's say the line y equals to A on the axis, and we just get some sort of straight line. That's the line y equals to x. So for example, at 1, we have 1. At 2, we have 2, so on and so forth. If I draw the graph of y equals to the rounded value of A, it's quite simple. Up to half, up to there, up to half, up to half. From 0 to there, you've got nothing. Then between 0.5 and 1.5, you go up to 1. And then between 1.5 and 2.5, you round to 2. And between 3.5 and 4.5, you round to 3. And so on and so forth. So if I wanted to replicate this, but with some factor, let's call it n, times A, it would actually be very simple. The whole graph would just be scaled in the x direction. I know this is not continuous, but you can apply some basic transformations to it. It would get scaled down quite simply. And so then this number there would be 0.5 over n. This value there would be 1.5 over n. This value there would be 2.5 over n, so on and so forth. And so it's quite simple to turn this into a formula. Basically what we can find is that the rounded value of some whole number multiple of a decimal a is going to be some whole number k, and remember obviously it's always going to be a whole number, some number k if a is between the values of, so for if we just do a couple of examples, it's going to be 0, or we'll leave 0, it's going to be 1 between one lot of 0.5 over n and 3 lots of 0.5 over n. It's going to be 2 at 3 lots of 0.5 over n to 5 lots of 0.5 over n. That's there and there. 5 lots of 0.5, 2.5, 3, and so on and so forth. And so we turn this into a formula. It's 2k plus 1 over 2n and 2k minus 1 over 2n. And so we can put this into practice quite easily. Let's do an example again. I have some n, let's say 36, I don't know. I don't know what a is, and I've rounded it. So let's say I've taken 36, I've timed it by some decimal number, and then I've rounded it, and I know that the answer is, let's say 8. And the question is, what is a? So yeah, we can solve this fairly simply. We know that it equals to k, and so basically we know that a must be between 2 times k, 16 plus 1, 17, over 2 times n, which is 72. And it must be bigger than 2 times that minus 1, so 15 over 72. You can put this in and verify quite easily. If we do n times a, that's going to be the rounded value of 36 times 15 over 72, or 17 over 72. So if we just work that out, what 36 times those are, you get 15 over 2 and you get 17 over 2, which are 7.5 and 8.5 respectively, which makes sense because we know they're supposed to round to 8. And so yeah, that kind of verifies that it works. So we have our maths. We had, I think it was 45a must be equal to 49, the buffed value, minus whatever we project the flat increase to be. And we're going to just put in test values of like 1 and 2. So for example, for a test value of 2, so 20 raw flat added for attack up small, element of small, then 45a rounded would be 47, which would suggest that a would be somewhere between 1.033 and 1.056. I did that calculation off screen quickly just on the calculator. And so, to determine the values of a and b that are correct, what we can do is repeat this process for every value of b and for every single setup we have. So for example, we had the 55 buffed to 59 version. That would give us some boundaries for a given different test values of b. So this would be the b equals to 0 test value, the b equals to 1 test value, the b equals to 2 test value, so on and so forth. So we can work out all of these ranges, and then we can repeat it again for the 720 to 791. You'll see that in the spreadsheet. I'll go back there in a second. But yeah, so that's how we get a whole bunch of possible ranges of a. Now to further work out which one of these ranges is actually accurate, what we can do is, for example, so let's take the b equals to 1 range. We can take all of our possible ranges of a that we worked out, of the multiplier, whatever, and we can combine them. Imagine you had a number line, it's fairly simple, and you had, I don't know, these intervals. You could quite easily take the overall one that satisfies all of them. You know that a has to be somewhere between here, right? And so hopefully that isn't too confusing. But yeah, that establishes a range of values of a. And so what you do is you take all of the lower bounds and you find the biggest. You take all of the upper bounds to the limits and you find the smallest. And then that'll give you your range of a, your sort of broken down one that's a lot smaller and more accurate. Now, we've got 5 sets of calculations. Hopefully that's enough to isolate the right answer. And the way that we're going to isolate things is by using the fact that, let's say we instead got a number line like this. We know A has to be somewhere between here and here, A has to be somewhere between here and here, here to be somewhere between here and here, and then the fourth one was A had to be somewhere between here and here. There's no way that all four of these regions can be satisfied at the same time. You can't pick a value. So let's say we pick a value, I don't know, here. That matches three of them, but it doesn't match the fourth. Or you pick a value here and it matches the fourth, but it doesn't match the three of them. So this would be an impossible solution. This would be a possible solution. And so any impossible solutions, if we get them, what that means is that our original estimate of B is a bad estimate. It's wrong. It's not possible. There's no way of B. Now I'm hoping that without, well, I know actually because I've done this before, but our 5 sets of values are enough. I had to get the fifth one separately, specifically because it wasn't enough. But yeah, it's enough to isolate the right values of B and A. And so after this entire process takes place, we'll have a hard value of B sorted, and we'll have a range of values of A. And hopefully this range will be fairly small. You can make it smaller by doing more testing, but I just want to have sort of rough numbers to test with. So they'll be right to within like 2 decimal places or something. And so let's say we have a value of A. And so from this, we can work out the buff. We know that the buff is A times our elemental buff, elemental stat, plus the flat buff. And we can do that for every single buff type. So element up small, element up large, etc, etc. And so just to show you what you're missing out on, because my last video recording corrupted, this was the formula that I was originally using. And so you'll see references to things like K2 and delta and N2 and N1 and all that weirdness. Don't worry about those. Don't worry about those. I'll explain the spreadsheet when you see them, but just ignore those. Those were from the previous attempt, but I've refined the method. And so you don't have to worry about this complicated maths. And so here we are back in our spreadsheet, again with just all of our raw values listed out. I have the ability to control which builds I'm looking at. So for example, we can compare build 1 to build 2 with 1 and 2 referring to these numbers here. 1 and 2 was the 450 and 550 ones. And so we're comparing 450 and 550 to their buff values 540 and 660. The reason we picked 540 and there we go, 540 and 660 are because I've asked it to do element up, effectiveness up plus element up large. However, for now we're just going to go with element up 1 just so I can show off the calculations. And so yeah, back to 490 and 590, our example values. So yeah, ignore all of this weird K2 nonsense. What's going to happen here is our projected value of B is going to go. So actually, let me just make this green as an input. We're going to choose the value of B. So for example, we project a value of B of 3, so 30 true element. We work out our 4 intervals of A for each of the builds, like I explained in Microsoft Paint. And then what we do is we do our process where we pick the biggest of the lowest and the lowest of the biggest. Now, this width interval here is basically an indication of what I was talking about, how we can reject them. So if it's negative, it means that we've got those intervals that don't overlap nicely. Whereas if it's positive, it means we have an actual region that satisfies all of the conditions. What this means here is that B equals to 3 is completely impossible. And so we can try B equals to 4, still impossible. B equals to 2, not possible. B equals to 1, not possible. B equals to 0. Oh, okay, and it's possible. We've got a value bigger than 0. And so actually this answers it. This is a range of values. We don't actually know specifically what value A is. It could be anywhere from 7.78% to 1.081, so 8.1%. I've worked out the average here, but this is the value I'm going to be using. Given that this is the developer stuff, it's not some arbitrary number they've picked. It's probably 8%. And it's just a little bit of error. Again, you could lower these errors by getting more builds, testing the values and putting them all in here. But yeah, so hopefully that explains the method. I picked projected values of B, use the rounding calculations to then estimate what A must be. And so that is where this value comes from, the value and the error. I blanked them off because you wouldn't know where they came from, but hopefully I put a timestamp so that you could skip through the maths if you didn't want to see it. So yeah, let's get rid of that block. 7.98%, which is just that average value rounded, and plus or minus 0.2%. That was the width of the interval. As a percentage, half the width is 0.2%. So basically what this value says is the buff for element up is 7.98% plus or minus 0.2%, somewhere in that region. So it's somewhere between 7.8% and 8.2%. But I'm going to assume the average of roughly 8%. I was going to have a column for the flat increases, but the flat increases are all 0, so there's no point including them from here onwards. Oh yeah, actually I should mention for every single one of these buffs, there is no flat increase. So the hunting horn buffs apply purely a multiplicative, an element modifier. They don't do any flat additions of like 10s or 20s or whatever. So I repeat the process for all of them. I found that element up small gave us 8%, element up large gave us 10%, element effectiveness up on its own gave us roughly 5.28% plus or minus 0.28%. It's probably like 5% or 5.5%. I don't know. I'm just going to use the averages, so 5.28%. Okay, so if you stacked element effectiveness up plus element up small, it actually gave you a huge boost. It doubled from roughly 8% to roughly 16%. So 16.4 is the number I'm going to go with. 16.4%. I would say there are some rounding errors involved with these calculations, so be careful. This is mostly just rough values for my own purposes. I'm sure they've probably been data mined somewhere. I'll probably put them on screen if I find them. But I did want to show the maths just to prove that there was some testing behind my claims. And 20% for element effectiveness up and element up large. Yeah, really nice. You'll notice that the 10% value had no error, by the way, which is kind of interesting. But yeah, so 20% for large stacked with element effectiveness up. So these are all our values. Just an FYI, I looked it up and apparently it's 16% for element up small stacked with element effectiveness up. I'm not sure why 16 isn't included in my range of mathematically viable options. I think I made a mistake with the calculation process somewhere. So don't pay it too much mind. It's 16% basically. Anyway, the last thing I wanted to talk about were the way that this interacted with the element up skill. You know, for example, that at level 6 it gives you 100 bonus and a 20% increase, as we talked about earlier. I'm just gonna not bother explaining. I'm just gonna open these all up for now. So I ran the tests with this horn here, the 900 element one, but with dragon attack level 6 on the set. And so you can see that the base is 180, which makes sense. 900 divided by 10 is 90, so the true element is 90. 20% of that is 18, which takes us to 108. We add the 10 bonus, for 100 divided by 10 is 10. We add the 10 bonus to 118, and then you times that by 10 to get a displayed value of 180. So it makes sense, and then these are the values with the various horn buffs applied. Now I ran 3 sets of possible calculations using these numbers that I calculated here. First of all, I did hunting horn after the talisman multiplier. This is how I assumed it worked. So I did the 20% from the bonus times with the additional 7.98%. So you know, I would apply them multiplicatively, and then the bonus I would add after all other calculations. This one here is the hunting horn applies right at the end. So we do all of the bonuses first. So we take the 100 bonus and the 20% from the upskill, and then apply the hunting horn percentages on top of that. And the last one I wanted to try out was an additive multiplier. So I wanted to see if the multiplier is stacked additively. So rather than doing 20% increased and then 7.8% increase on top of that, I added them together to get 28%, and then I worked that out as an increase instead. And then I added the 10 on at the end. As you can see, the first set of values both do round to the right number with the element up small. However, past that you can kind of see that the only one that's actually accurate is after the talisman multiplier. The rest of these values are completely incorrect. They round to the wrong numbers. This, for example, rounds to 129, 1290, whereas this would be 1300. So yeah, basically it works kind of like you'd expect. It applies the 20% bonus to your element. So actually I can run this calculation for you just to show you how it works. We take 900, so we take 90. We then times that by a 20% increase to get to 108. We then times that by, for example, 7.98%. Well, actually I should do 1 plus that. That'll give us the hunting horn buff without the bonus applied, and then we add on our bonus of 10 to that. And so we end up with 126.6. That rounds up to 127, which gives us 1270. And we can just change the multiplier one time just to show you how it all works. Let's do, for example, element effectiveness up plus attack up small. So we take this, instead of doing D1, we'll do G1. We end up with 135.7, so that's 136, which is 1360, which is exactly what we'd expect. So yeah, that's how the hunting horn buffs stack up with skills like that. So yeah, hopefully I've covered everything. This is mostly just a precursor to my Alatreon defensive skill, the whole element conversion thing. I'm going to be testing that with some hunting horn buffs to get some more accurate numbers. Yeah, hopefully this all made sense. It was kind of an excuse to just sort of do some interesting rounding related algebra and sort of do a maths video at the same time, kill two birds with one stone. Yeah, let me know if you have any questions, but otherwise I hope you have a lovely day. Take it easy. Bye-bye.